Hello again. So this is example 4, so the fourth application of electrolysis, which I was I was meant to tell you on Tuesday, but the videos were getting way too long, so I thought I'm going to do this today. So the fourth application is electroplating, and this is a very, very specific application. This is not to produce a material, but you essentially, as the name suggests, want to coat an object with a thin layer of metal. So you may want to do that. Say in this case, I found this photo which I thought was hilarious. That looks like teapots or something like that. So maybe, for example, you want to electroplate an object with, say, silver to protect it, and also for aesthetics. And then I think these are bits like parts, and I think that this is a nickel solution. So this is being electroplated with nickel. All right. So in general, if you want to electroplate an object, the cathode is the object to be plated. This is compulsory. You'd have to have the object to be the cathode. The anode, well, you don't necessarily need this, but a lot of the time the anode is the metal to be used for plating. So I'm just going to say, so this is required. But having the anode being the metal used for plating is not necessarily required. It's probably optional. If you don't use it, then it's going to change one thing. I don't think I'm going to talk about that in this video, but we're going to just stick with the anode being the metal. So cathode is the object, anode is a metal, and the electrolyte is a salt, or well, salt is just another name for ionic compound. That's not how you spell ionic. So the salt of the metal to be used, so an ionic compound of the metal, and this is also required. So if you want to achieve the electroplating, you need the object to be the cathode, and you need the electrolyte solution to be the salt of the metal to be used. Probably very hard to have a molten electroplating process, because you probably will melt the object by the time you electroplate it. So you can't really electroplate anything that is a weaker oxidizing agent than water. So anyway, and obviously you need a power supply because this is electrolysis. So I have a diagram here. So let's say we're trying to plate copper onto this coil, if you will. So this is the object, and the metal to be plated is copper. So I'm using copper as the anode, and I'm also using a solution of copper with a power supply. You don't need any separation of the cells so that the products are separated from each other. I will show you why in a second. And actually, let's talk about what happens in this cell. So we're going to list everything that's present. Now, I wrote nickel here, but a lot of the time the object is like a compound, a mixture of multiple things, but the object is not going to participate in the reaction. For all intent and purposes, you can assume that this object is inert, because also if it's a metal and it's connected to and it is a cathode, it's not like it can do anything. So assume that the object is inert. It's okay. So this is the cathode, which is the object, and this is the anode. In this particular case, I have 1.0 molar copper sulfate. So it means that in the solution, I have copper 2 plus, SO4 2 minus, which we also will consider to be a spectator ion, so it's not going to react. And then we have H2O. So let's think about what happened at the anode, the cathode. Let's start with the cathode. So at the cathode and the anode, you have copper. So those are the 4 species present. At the cathode, if we just think about everything that's present, there's water, cathode, and there's water down here. So there are only 2 oxidizing agents present. You have copper ions in the electrolyte and water in the electrolyte. And copper ion is a stronger oxidizing agent. So what happens at the cathode is copper 2 plus is going to get reduced to produce copper. And you really need, in order for the electroplating to actually happen, you really need the product of reduction to sort of stick onto the cathode. So it's going to stick on this nickel, so the copper is going to stick on here. So that's what happened at the cathode. And then at the anode, I don't have any, anyway, At the anode, in this particular case, because the anode also have metal copper, so at the anode, you're going to have copper, because if you consider copper and water, copper is a stronger reducing agent. So copper is going to get oxidized at the anode. Where am I going to write that? Okay, so anode. So this is really interesting because it's essentially the same reaction, but you just reverse it. But this only applies because you're using the metal as the anode as well. So copper going to copper 2 plus and 2 electrons. So you're using up copper ions on this side, and then you're releasing copper ion at the anode. All right, let's just show you that in a little bit more details. Oh, this is the experiment you're doing today, by the way. So I need to show you the setup before you can start the experiment. So I made a quick diagram of this, even though some of this is kind of unfortunate choice. This is the object. So this is the cathode again. They connect to the negative terminal of the power supply. The anode is the metal, and then you have a solution of copper ions. I'm not showing water or sulfate ions in this diagram. It's just going to get way too crowded. So let's focus on the object first. At the cathode, you're going to have electrons coming from the power supply, and it's going to go through the object. So the object has to be able to conduct electricity, and the electrons, or 2 electrons in this case, is going to be accepted by the copper ion that is on the surface of the object. And that is going to turn the copper ion into copper. And the copper is going to stick onto the surface of the object, hence achieve the electroplating purpose. So in order for this to work, that's just what I just said. In order for this to work, the object needs to be able to, well, the copper has to be able to stick onto the object. So a lot of the time when you do the experiment, and I hope one day we actually get to do it in class, is you have to make sure that you clean the object really well so that it doesn't have any grease or anything on it, especially if you're copper plating I think we normally do 50 cent coil. You have to make sure that it's as clean as possible so that it's easy for the copper to stick onto the object. There is a chance that the copper just falls down, and that's one of the inaccuracy of this experiment. So the object, the cathode, must be clean for copper to stick to it. But you can never guarantee that 100% of the copper is going to stick on the surface of the cathode. You have to clean it really well with like acetone, but still. Now, on the other side, with oxidation, some electrons will be pulled out of copper. So electron is going to go this way. I'm just going to redraw that again. So 2 electrons going in here, and 2 electrons will go out of the copper on the other side to become, and then the copper becomes copper ion. And the copper ion is going to go into the solution. So what you can see is that the anode is going to decrease in mass over time. And if you do this experiment, you should be able to measure the change in mass of the cathode and the anode. If everything goes well, then the loss in mass at the anode has to equal to the increase in mass of the cathode. So mass gain at cathode is supposed to equal to mass loss at anode, but you almost will never see this. There will be some, most of the time some of the copper will just go to the bottom of the solution. You can almost tell later when you look at the solution, you see like really small bits of copper. But theoretically speaking, they should be equal to each other. I think the one more thing I want to say is the movement of the ions. So as you can see here, so copper ion is being consumed at the cathode, and then you're producing copper ion at the anode. So copper ion is going to go towards the cathode. So that's the movement of ion in this cell. And this drawing is not great, but obviously there's copper ion here as well. So flow of ion is that copper ions will be produced at the anode and flow to the cathode. But the main thing is that the concentration of copper sulfate in the solution will be constant, because the rate of consumption of copper ions at the cathode should equal the rate of production of copper ions at the anode, considering how you are essentially having the same reaction but just reversed. I think that's it for this electroplating process for now anyway.